All right, let's get going again. So when we were in the high pressure limit, where we assumed everything was thermalized, it was pretty straightforward. We just did the calculation. We got did the Boltzmann average. We got the rate. But if we can't do the Boltzmann average, we have to keep track of the energy states. So when A plus B combine, we have to keep track of how much energy A and B had, so we know how much energy the product will have, because energy is conserved, right, when these two guys hit each other. And there'll be a lot of possible energies, because A and B are probably sampling from a Boltzmann distribution, yeah?
So what is the criterion to decide that when we need to consider this effect?
What matters is if this rate of this thing falling apart, kd of E, if this is comparable to or larger than the collision rate, then this is very important.
So usually it happens when they have a huge energy difference. Or the transition state barrier is short. But
well, so like you can see in this geometry, in this kind of surface, A plus B are coming in and forming the AB complex, AB reactant in different energy states here. And the key is the reverse. Now the reverse rate, Kd of E, is the number of states of the transition state of E over H rho of the AB, this guy, of E. So the number of transition states, this thing is always going to be close to 1 or 2 or 3, because a lot of the AB reacting are going to just barely creep in over the barrier. So this is always some number that's sort of same scale, maybe 10, 100, I don't know, 1, something like that. This rho can be wildly different. So rho scales as E to the number of vibrations power, something like this. And so if you have a big molecule, this thing grows wildly fast with energy. If you have a small molecule, it doesn't grow so fast. It can be a lot smaller. So for a small molecule, if AB is a small molecule, then the rho will be small, and in which case the K will be very large. So the smaller the molecule is, the more likely this is a problem. So in the extreme case, hydrogen, you have H plus H atom to make H2. It's always in the extreme low pressure limit. It's always extremely non-Boltzmann, because the Kd is so gigantic, because the rho is so small. But if you have two gigantic soot particles bump into each other and stick, they have, each have 100,000 carbon atoms in them. They have zillions of vibrational modes. So the rho is huge, and so the whole rate of them falling apart will be very small. So there'll be plenty of time for that to live and before it falls apart. And during that time, it can suffer collisions and lose energy. If you're interested in this general topic more generally of how to quantitatively tell if your reaction is going to be pressure dependent or not, I wrote a paper about this. I think it's B. Wong, D. Matthew, and me. J. PhysChem, maybe 2004. I'm not sure exactly what year. Something like that. J. PhysChem A probably. And there's a whole paper. The title is like, when am I in the high pressure limit? And it gives you approximate formulas for your particular case. It depends on how many atoms you have, how deep this well is. So the deeper this well is, the bigger rho will be, because this is the energy that comes in to the rho calculation, is the energy from the bottom of the well up to there. That's actually a good point. This formula says the same E, but they're sort of like reference different things. The E that matters for the transition state is the E above the barrier. The E that matters for rho is all the way from the bottom. So if this well is very deep, then usually the rho will be very large, which means that the K will be very slow. So then you'll probably be in the high pressure limit, because you'll have plenty of, the rate of it falling apart will be very slow, and you have plenty of time for it to suffer a lot of collisions to get thermalized before it falls apart. But if this is shallow and there's not very many atoms, then this rho will be tiny, and then the rate will be super fast, and then you'll never be able to collisionally stabilize it, even at 1,000 bar. right? All right, so this is so very important to know what KD of E is. So we know the K forward of E. We can evaluate this from the RChem expression as well. Or we could just use the KD of E and use the ratio of the rows. Do you remember? Because we said that rho of the reactant times K forward is equal to rho of the product times K reverse. Right? That's the detailed balance. So you can get that number. And then you have to figure out how fast do you lose energy when you have collisions. And in interstellar space where there's no collisions, then it might be photon emission, that the highly vibrationally excited AB those vibrations might radiate infrared photons, and that would be a way to lose energy as well. All right, and so the overall rate that you see for how fast AB comes together and actually makes a stable AB is going to be some complicated combination of all this stuff, where this is the probability of the collision taking away some amount of energy. Kc is the collision rate, how often it collides with a bath gas to thermalize it. And so this is kind of a mess. So I'll try to explain to you how we handle this mess. So originally, the first people to realize this problem were Lindemann and Hinchelwood. And they decided to write it this way. So they said, OK, A plus B forms this pseudospecies, AB excited. The pseudospecies falls apart back to A plus B. And the pseudospecies collides and loses energy and gets stabilized. And they said, well, every collision stabilizes it, so K collisional is what they use there. But then what they do is kind of goofy, is they said, well, that these things, K forward is a function of temperature. That sort of makes sense, because these are both thermalized. But this guy is not thermalized, but they still have this thing as a function of temperature. So something's a little strange about this whole treatment. But that's what they wrote back in their paper. I think it was the 1930s or 1940s, something like that. And then they did a steady state approximation, quasi-steady state for AB star. That's OK. So you say that this guy is about 0, and you get the K effective you say AB stars is about 0, and you get this formula. So it's K forward, K collisional over K decomposition plus K collisional. And so then in the high pressure limit, you get the correct result you expect, the K forward, which is the normal reaction rate, which we get from the Boltzmann value, Kf of T. And in the low pressure limit, you get this ratio. This whole analysis, because of this crazy KD of T thing, and also they never keep, the different ABs have different energies, which means they have wildly different lifetimes, the AB stars. See these guys, the excited guys, there's not just one of them. They're all different energies. And remember, they all have different rates at which they fall apart. So this, you have an AB star over here, but the AB star with this energy only lives very short time. The AB star with this energy lives a lot longer, has a much shorter dissociation time. So you really have to treat them separately. You can't just treat them as one species. And there's no way for them to exchange energy between them because there's no collision. They don't live long enough to have collisions. So you're stuck with one or the other. So they're really different species. So this analysis isn't quite right. But good for qualitative thought. And so if you read a textbook, usually intro PChem textbook, they always give this model. It was good enough that it matched the crummy experimental data they had available at the time when they did the model. And it resolved it. There were a bunch of even crazier ideas that were suggested to explain the experimental results, and this it was much more rational. So this became very popular. So then when Marcus wrote down the RKM theory for K of E, which is the correct formula for K of E, he said, we really should put K collisional with KD of E instead of KD of T, because he said the decomposing AB star species doesn't have a Boltzmann population, doesn't have a temperature. So make a KD of E instead. And so it goes inside the integral. You integrate over all the energies, and then you get this expression here where the collisional thing is inside the integral. We're doing sort of an average. This is the end of the transition state, this Boltzmann average, and now we have this guy inside here. And so this one looks OK, and you can integrate it, and everything looks OK. So this one is sort of semi-reasonable. And so this was much more successful to predict things than the Lindemann theory. And so this is very popular for a long time. However, this collision, assuming that every collision takes away all the energy, is a little excessive. So people corrected it and said, well, you know, some collisions are pretty much elastic and don't take away much energy, so they can't cool the thing down. So let's say only some fraction of the collisions are hard enough, strong enough to take away enough energy to make much difference. So let's call the fraction beta of the collisions are strong enough. And Troa did an analysis for one really simple case and came up with some formula for beta. For some simple case that he could do sort of analytically, figure out what beta should be, considering all the possible amounts of energies that could be exchanged. And so people use his formula for beta that he did for that one simple case and use it for all cases, because it's the only one we have an analytical expression for. And that thing is called the modified strong collider approximation. So instead of just a strong collider, now you have a modified. The beta number turns out to be typically about 1/10. So it's usually about, if you live long enough to suffer 10 collisions, usually the excited guy loses enough energy that's not going to fall apart. And that's the rule of thumb is about right. And when you do that, then you get results that are pretty reasonable. So you have, this is the K effective formula. You can look at the low pressure limit. Very interestingly, in the low pressure limit, you get a result that is independent of the transition state. So it only has to do with the density of states of the species you're forming, and it doesn't have anything to do with the properties of the transition state. But it depends a lot on the threshold energy. And this method is pretty good and easy. So I would say this is one of the recommended methods, I think. And actually, I have in my RRMG software, we have an automatic calculation using this method. And I think in our experience, we've never been off by more than a factor of 3 from the exact solution. So if you want a ballpark number that's easy to do, this is it. But of course, you could be off by a factor of 3. So you could pick up an extra factor of 3 error because of the way we're doing this beta thing. The beta is kind of fishy, right? Where the heck do you get one number to figure it out? So a lot of people were unhappy with that. And they said, look, let's write the full master equation. So when you look at this problem, this is terrible. At MIT, they go down. This is why Princeton is not MIT. All right. All right. The way to look at this is I'm interested in the population of one energy state. So here I have, this is the number or the number of molecules of AB that happen to have this energy in this range. Energy is less than some delta. Right? There's a certain number of molecules of the AB star that are formed that have energy in the range around E within delta E of E. And so I want to calculate them, and I want to do a population balance. I want to say how many of these guys fall apart. So I can write down the KD. I'll give a rate for how fast they're going out. I can write a rate for how fast they're being formed, because they're being formed by A and B. If these guys collide and react and have the right energy to fall into this bin, then I should count them as forming it. And I also can have collisions. Collisions, I could collide with a bath gas and get cooled down. And there's many possible states that I could end up in. Or I could even get knocked up. I could take some energy from the bath gas and go up. And overall, because I'm above the Boltzmann distribution, I would expect most likely I'll knock down. If I have a collision between my nitrogen molecule and my reactive complex is really vibrating, so most likely it's going to give energy to the nitrogen, but it's possible the other way around. Maybe I hit a very hot nitrogen molecule. But if I can keep track of all these possible things that can happen to my state, then I can do a population balance in this guy. And then if this guy gets knocked down, it forms another one here, and I can do a population balance on that one too. And I can write down differential equations for all these different possible bins of A, B of E. And so those are called the master equations. And this is the form of it. And let's see if we can look into what this is. So here's the collision rate. Here's how much collider I have. So this is like kinetic theory of gases. How often do things hit? It's sort of Kc times how much pressure you have. And then this P of E prime is a probability that if I had some energy E prime, when I suffered a collision, I would change to have energy E. And this is if I have energy E, what's the probability when I have a collision, I'll go to E prime. And so, and then I want to integrate this over all possible E primes. And so that accounts for all the collisional energy transfers. And then I also can have it just disappears because it's decomposed. And actually, there should be another term here that I add that it could be formed from A plus B. So I have chemistry at the end, and I have collisional energy transfer in the beginning here. And if I put them all together, then I have the master equation for the populations of all the different energy levels. And you can do some normalizations. You know some properties of P, E prime in order to satisfy the fact that if you let this run for a long time, and if there was no reactions, if these were 0, this thing has to give you a Boltzmann distribution in the end. So therefore, you have some relation about the P, E primes that they have to be somehow related with the Boltzmann factors, rho e to the negative e over kt, so that in the end, if you gave it a Boltzmann distribution, there would be no change. The population would be stationary, right? Because that would be the equilibrium situation. Here's the reversible formulation. So here's the forward rate, here's the reverse rate, decomposition, formation, and all the energy transfers. So it's just a system of differential equations. You guys have done these a lot before. The interpretation I told you was the number of molecules here, the n, but another way to think about it is the probability of finding the system in a state. And this is sort of similar to PDF methods in CFD. Do you guys know PDF methods, anybody? Turbulence. Yeah, turbulence modeling, yeah. Yeah, so there's also, you're doing a differential of a probability. So here's the differential of the probability of finding the system with A and B together with a certain amount of energy. All right. And now you have this differential equations. Because of the fact that you know what the equilibrium solutions are, you can normalize this in a clever way, and it makes the matrix symmetric. So you have ddt of your probabilities or your populations is equal to some matrix times all the possible populations of all the states. And you can write it in a way so that this G is sort of do a change of variables to make this a symmetric matrix. And that's very convenient because this is now a problem you can solve by eigenanalysis. So if you diagonalize the matrix G, find the eigenvalues and the eigenvectors, then you can rewrite this in a very beautiful way. Here's the solution. So these are the eigenvectors of G. This is your initial condition. And these are the eigenvalues of that matrix G. And because it's a symmetric matrix, these will all be real eigenvalues. And in the normal cases, all of them are negative. So the whole system is like decaying. And the one with the smallest magnitude, which is the slowest process, that's sort of the rate controlling step. And in a case like this, that would be the one that corresponds to the reaction. So the slow process, the really slow process here is if I started with here in the Boltzmann population, it's very slow to go all the way up and go across that huge barrier. So that's the slowest process there is. The eigenvalue that corresponds to the slowest time constant is that one. Is about how this thing is very slowly decaying away. And the fast ones have to do with the collisions because some of the collisional energy transfers are really fast because every time a nitrogen molecule hits it, the energy transfer changes a little bit. And so you get a whole bunch of fast eigenvalues that have eigenvectors that correspond to collisional energy transfers. And so that's what you have. Now you have a lot of, how many eigenvectors and eigenvalues do you have? It depends on how you discretize the energies here. So I break this up into a lot of different energy states, E, E prime, another E, another E, another E, lots and lots. Maybe 500 or 1,000 different energy states I consider when I discretize the equations. And so I'll have like 1,000 eigenvalues, and each eigenvector is 1,000 entries. So it's slightly confusing to look at when you run it. But to start with, you only care about the slowest ones. I'm just trying to get the decomposition rate. Once I know the decomposition rate, which is the slowest one, I can use my microscopic reversibility in the thermo to compute the reverse rate. And so if that's all I care about, that's all I'm done. So this is easy.
How do you know P bracket EIJ?
Which one?
The
Previous slide?
P.
Yeah, good question. Really good question. Maybe we'll skip ahead and answer that question. Collision rates. Okay, so first we do collision rates. A lot of people use Lennard-Jones as an approximation to the collision rate, even though maybe it's not really true. But we don't really know what the collision rate is, so that's what they do. And there's a formula for it. Some people just use hard sphere. I don't know. As you'll see in a minute, we know even less about the energy transfer. And this is actually a very crucial, unresolved scientific question. So a lot of people will use this formula and say that the probability of the energy transfer depends exponentially on how much energy is being transferred. This is used a lot, and there's a sort of rough argument that it should sort of be like this. And also, there's some experiments that sort of look like that, where they, one thing you can do is you can take a molecule, you can excite it, say with shining a photon on it, and then you can measure how fast it loses its energy. Or you can measure how fast the gas around it gets heated up. And from those, if you can analyze the molecules that it's bumping into and how they're changing their energy states, you can kind of get an estimate of the delta E per collision. And so you can see if it's a probability of having a big delta E or a small delta E.
Does that need to take into account the geometry for the two molecules that are colliding, or is it just raw energy?
Well, in that experiment, you have one molecule like AB, and you just shine a photon at it, and now you have excited AB. And now you just look at the collision partners, the nitrogen, and see does it start vibrating with a Raman spectrometer, for example. And what you see is instead it doesn't really vibrate. What it does is it starts to rotate because the collisions don't transfer that much energy to make a nitrogen vibrate. So first guess, this was pretty good. And as of what people knew 15, 20 years ago, that was all we knew. And the nice thing about this model, it only has one parameter, which is this alpha thing. And people did a lot of cases, and they tried to figure out what value of alpha would have to be to explain everything they saw. And they always get alpha values that are in this range, sort of 50 to 400 wave numbers. Okay? But they usually don't really have proof that it's really this shape. They just know that you get the overall rate correct if you take alpha in this range somewhere. But different experiments would get different alphas. They wouldn't, some people get 50, some people get 120, some people get 240. So who knows? And then some people decided that it has a t-dependence. They did the experiments at different temperatures, and it wasn't quite linear. And so sort of maybe 0.85, I don't know. I don't think there's any theoretical reason why it should be 0.85. So this is sort of the status that people from experiments have sort of inferred that maybe it's like this. However, there's some other experiments that show that sometimes you get gigantic amounts of energy transferred in the collision, much bigger than you'd expect from the exponential down. And so those are called super collisions. And there's a big debate about exactly what physically happened that causes a single collision to transfer so much energy. And so I'd say this is like an unresolved thing. But I'd say recently there's several experiments that show this kind of double exponential behavior. So that looks sort of like it might be true. But I don't know. And sometimes you don't see it. So anyway, and the super collisions are not very likely. So you have a lot of collisions that don't transfer much energy. And then no collisions transfer money whatsoever. And then people said, well, maybe it's not really double exponential. Maybe it's a Gaussian. So they tried to fit this way too. And I don't know. So maybe one of you guys can figure out how to do the experiments to really nail down what this is, or to do the calculations. And so some people try to do calculations for this. They've done a couple cases, look pretty good. But I would say this is not resolved at all, really. So this is an active research area to try to figure out what this is. Most people, what they do is they use this form because it was historically the one people use the most. And people have done enough experiments to get these alphas that they must be somewhere in this range. These guys are kind of weird forms, and nobody knows what the alphas really should be. And this one has 2 parameters, alpha 1 and alpha 2. That's worse, because then I don't have enough information to even determine 1 parameter. So they don't like that. But anyway, this is a big weakness in this whole analysis. And this gives errors maybe factor of 3. It's kind of uncertainties. If you vary that range of alphas, the consequences on the rate are something like factor of 3. All right, so.
Is this the biggest error?
Well, I don't know. So I have a factor of 3 if you use this modified strong collision compared to master equations. So there's one factor of 3 there. Here's another factor of 3 from the fact that we don't know what the collision model is. So that's 2 of them. Keep going. I'll tell you some more errors in a minute. All right, so problems. There's numerical problems in solving the master equations. So unfortunately, the master equation matrix is like stiff. So there's a collisional time scale, which is super fast, particularly at high pressure. You do like a diesel engine, the poor molecules get being bombarded, every like picosecond is getting bashed by some molecule. So you have 10 to the minus 12 second time scale. And then the dissociation rate of the molecule, if it's like, say, a cetane improver, that dissociation rate might be milliseconds, so 10 to the minus 3 seconds. So it might be 9 orders of magnitude difference in timescales. So that corresponds to the eigenvalues also differing by 9 orders of magnitude. And most of the eigenvalue solvers can't handle 9 orders of magnitude difference between the eigenvalues. And so you'll end up getting crazy stuff. So a lot of times, instead of all the eigenvalues being negative, which they must be physically, you'll get some of them positive if you just send it to a regular eigendiagonalization program. So some people found that if you can use quadruple precision in your eigensolver, then usually this is not a problem. It can handle 9 orders of magnitude. Unfortunately, not many people have a quadruple precision eigensolver available to them. So this is of limited practical use. But maybe with the new chips, now they have these chips, how many bits do you have in the chips? 64. So maybe with 64 bits, you could just do it. But just the problem is that the numerical libraries were not written for quadruple precision. So, and the math coprocessors and stuff, a lot of them are not made for it. So anyway, but maybe eventually this will just be routine. Currently, this is not so easy. Some people integrate the master equations in time because there's really good stiff solvers. So instead of doing the eigenanalysis, you can just do a stiff integration of the ODEs. It works fine. You get the numerical solution perfectly, no trouble. The problem is trying to interpret what that means. So you get 1,000 energy states that are all decaying with different multi-exponential decays. And now you're supposed to somehow turn that back into a rate coefficient. And it's not so easy to figure out what that is. So there's an issue there. And then some people say, well, when this guy has some collisions and gets knocked down, let's assume it's irreversible. So wham, it gets knocked down here, and it's so long that it takes it to come back up that let's just assume it's irreversible, it's gone. If you do that, it turns out you can reformulate the equations as a linear solve instead of an eigensolve to get the slowest eigenvalue. There's a special trick to do that. And it turns out that the numerical codes for stiff linear solves are much better than the numerical codes for stiff diagonalizations. So the numerical codes can handle it, the stiffness. However, it's only in that limit where it's true that it just goes down. So for a deep well, that might be okay. But for a shallow well, that's not true because it goes down and it comes right back up if the well's shallow. All right, and another problem is high temperature, particularly for shallow wells. The Boltzmann shape doesn't look like what I wrote there. The Boltzmann shape might start to look like this, where a lot of the Boltzmann peak is actually above the barrier. If you just computed what the Boltzmann distribution is, if the temperature is high enough. So in a burned flame, adiabatic flame temperature, 2,500 Kelvin or something, you might have the whole population is up here. And now you have a problem is that like a lot of your mass is in stuff AB star that's like above the dissociation limit. It's probably only living for picoseconds. How the heck to handle this? this has caused us a lot of confusion about how to analyze what the results of the master equation mean. And so here's a picture, like for methane, how the Boltzmann population changes the shape as you increase the temperature. So you can see when you get up to like 4,000 Kelvin, you have a significant fraction of the population is above the dissociation limit for methane. If you do it with a peroxy radical, even at 1,000 Kelvin, you already have a big fraction of the population that is above reaction barriers. And so this is a problem. Another issue is that the whole analysis so far assumes that energy is conserved, but it neglects all the other conservation laws. In particular, it doesn't consider angular momentum conservation. So if you have an A and B smash into each other, they should conserve angular momentum. So there should be quantum numbers associated with angular momentum that are conserved as well. But in the analysis before this, you would just glom all the different angular momentums together somehow in an unphysical way. There can also be other things conserved. So for example, if the nuclei have nuclear spins, the nuclear spin quantum numbers are also conserved during reactions usually. So if the hydrogen has a nuclear spin a certain way, it's not going to do a spin flip during the reaction. When you do that, then you now have to say, oh my goodness, now I need to keep track of the population as a function of energy and whatever the conserved quantum numbers are and time. And so now I get a much bigger matrix because each of these NEJ states need to be represented by as a different state of the system. And now in principle, I have collisional energy transfer of energy and momentum, and angular momentum. Every time we collision, I could transfer angular momentum as well. And so that gets complicated. And in fact, the rates could also depend on the angular momentum. And so now this gets to be kind of time consuming and complicated because now the matrices are getting just too big to handle. And also, we don't know enough information. We don't even know enough information to reduce the energy transfer, much less the energy correlated with the angular momentum transfer. So there's people doing experiments to try to measure this, but I would say we just don't know. And so you can do it. You can do it's called the EJ model, where you write down the rates, function of energy and angular momentum, and you write down, here's the collision rate. Anyway, you can just do the whole thing, just like you would expect. It's just now you have another index. Instead of just E, you also have a J everywhere. So that's one way to do it. Another model says, the angular momentum is conserved. That means that the energy that's associated with the molecule rotating around is not available to help break the molecule apart because I have to conserve that energy. So I say some of my energy is no longer available to do anything else. It's only available to rotate. And so then I have a different energy as epsilon. That's my total energy minus the amount that's tied up in rotation. And so then you can work out the whole analysis that way. And now you do everything in terms of these epsilons. I only care about the free energy, the energy that's available to me. I don't count the energy that's tied up in the rotation because of angular momentum conservation. And my calculation of rho is different then. And then there's a complicated issue about, for a normal rotation molecule, a big molecule with 3 moments of inertia, there's a Coriolis effect that couples the vibrations to the rotations. And studies show that Coriolis effect transfers the energy between rotation and vibration on a time scale faster than collision sometimes. And so then if that was true, then you have to allow some of that rotational energy to now come into vibration or vice versa. And what it does is it changes the total angular momentum has to be conserved, but the figure axis, the orientation of this asymmetric top with respect to the overall rotation can change, and that will change the rotational energy even though the total angular momentum is staying the same. So anyway, there's a way to handle that too. A little confusing. I highly recommend you read the papers if you try to do this first. And what you see what happens is that if the Boltzmann distribution was satisfied, this would be just 1. And what happens is the low energy states look like Boltzmann, but the high energy states near the barrier, the populations drop off because stuff is dissociating. And then you have a little tiny tail of stuff that has energies above the barrier. And this is kind of typical. And this is the steady state solution. After you've run some collisions for a while, you get into some kind of steady state where the stuff's reacting. You don't have any population at really high energy states because they fall apart too fast. They never even get populated. And but you start seeing a dip in the Boltzmann, deviation from the Boltzmann distribution close to the barrier. And then there's some approximate methods that try to model this in order to make it easier to calculate the rates. Okay, let's get to some experiments. So this is for methane dissociating in the low pressure limit. And what you see is that this is the experimental measurement of how the dissociation depends on the temperature. And this is probably all at some pressure, which is not specified in my figure. Sorry, I don't know what pressure this is. And this shows that if you did a model using the strong collider limit, you get a higher rate for the dissociation because it means every collision would knock it all the way up. But that's not true. If you did the Maastricht equation solution, it doesn't quite match the truth. It should, right? And so then you wonder, this shows like deviations in our problem with our Maastricht equation. So it could be that the P of E prime, that energy thing is wrong. It could be our collision rate expression is wrong. It could be other stuff is wrong. And so the Maastricht equation community is like working on trying to make this really exactly match with the experimental low pressure limit methane dissociation rate is. Here's another one, the low pressure limit of acetylene adding an H atom to make vinyl radical. The reverse of this is very important for making soot in flames. And you can see how the 1D Maastricht equation with just the energy conserved and the one with the energy and the J conserved, they're not that different. They're a little bit, maybe a factor of 2, something up there. So a lot of people would just do the 1D because it's easier. And it's not that inaccurate. This is a very important concept, fall off. So we said that this effect saturates. When the pressure is high enough, then if you have really, really high pressure, you should be able to force it to be Boltzmann distribution, no matter how fast the reaction is. And so at very high pressures, then you should expect this to be flat, that you become insensitive to the pressure, and you just get one rate, and that's the rate that we would calculate with the regular transition state theory. And if you're at really low pressures, then we expect that the rate of the reaction depends on the pressure linearly, because you double the pressure, you double how fast you're knocking things up, then you double how fast they fall apart. And then somewhere in between, it's got a curve somehow. And this shows the differences between the shape of the curve. So Lindemann-Hinchelwood gives this shape. If you do the 1D and 2D Maastricht equations, you get a much deeper dip here than the Lindemann model would say. And the level of deviations and what these things look like depends a little bit on the temperature. Sorry, we did this already. Yeah, actually, well, this is worth a comment. So when you read papers about this, you'll always see this thing, delta E with a bracket, or delta E with a D in a bracket. I just want you to understand what they are. So this one is one I really like. This one is the average amount of energy transferred in a collision that made the complex lose energy in a downwards collision. And so that doesn't count the ones that go upwards. Because remember, the collisions can knock the molecule to a higher energy state or a low energy state. Mostly it's downwards. And if you just compute the average this way, the average probability of knocking energy downwards, it turns out that this average number is approximately the same as alpha for an exponential down model. And so this is the number that people report a lot of times, is delta E down. Some people report delta E, which is the average energy transferred. This one's kind of confusing because some energy transfer is positive and some is negative, because sometimes you increase energy and sometimes you'll decrease energy in a collision. So it partially cancels out. And if your original case is pretty close to Boltzmann, it would be 0. So this is a kind of a strange thing. But you'll see some papers do that instead. And then for some reason, people do this one. I don't know what this means. It says like the root mean squared of how much energy is transferred. At least this one won't go to 0. So I don't know. Anyway, I don't know what that's about. Okay, so these are experiments for that H plus CH2, H plus acetylene going to vinyl radical. And you can see how the real rates are, a couple orders of magnitude lower than the K infinity, which is what the transition state theory would predict. But if you go to high enough pressure, you can actually get it up pretty close up to here. This is another one. This is for the reverse, the dissociation of the vinyl radical. And these are the experimental data. And I think these are different partial pressures of helium as a colliding gas. And you can see that in this case, the model and the theory are pretty close. And it's basically that you're in a low pressure limit, and the rate is just linearly proportional to how much gas you have. So the rate, here's 6 gas, here's 4, I think it's like 6 torr and, 2 torr and 8 torr. And the rate goes up by a factor of 4 between them. So that's sort of what you'd expect. People don't know the T-dependence of delta E down or the alpha. And these are different models for what would happen if you had different T-dependencies. And I don't know. It just shows we don't know what we're doing. People try to calculate the energy transfer from trajectory calculations by actually having a molecule in your simulation wiggling around and bashing it with molecules and seeing what the probability of the energy transfer is. And Jaspers specializes in this. And you get some results which look like some experiments. I don't know how much I believe it. But anyway, that's what people, that's like the state of the art. This is 2009. This is like a very active research area, how to do these calculations correctly. In the old days, Troa did some simple cases where you could do the analytical solutions and derived what the shapes should look like of these fall-off curves. So how you should do the intermediate region between the low pressure limit and the high pressure limit. What's the shape of the curve? And this is a form. This form is used in ChemChin. So a lot of you guys are probably using this now for simple reactions with a fall-off. It's not perfect. So typically, if error is 10 to 20%, that's not so bad. There was Ed Law, the organizer of this conference. He published a paper in 2009 suggesting a different shape that's a parameter-sized form that gives a better fit. So if you're not satisfied with 20%, then you can do that. There's still some problems. If you have a lot of tunneling, it screws up the shape. And how to handle that, it's not resolved. And then I'm going to talk more about multiple channels. So the Troa form was derived for a case where all you have is one possible reaction, say the dissociation there. But some of those cases I showed you have multiple things that can happen. And in that case, the Troa form does not work. What people sometimes do is they try to do what's called the log P form, where they try to interpolate log K as a function of log P. And that's in ChemChin. Sometimes this is good, but not always. And so here's an example of a multiple channel case. So this is a very important system. If you have a lot of methyl radicals in the flame, you have a lot of OH radicals in the flame. They get together, OH plus methyl. Sometimes the OH just abstracts an H from methyl, and it makes CH2 plus H2O. But most commonly, they recombine and they make methanol. And it's a pretty deep well, but the temperatures are so high in a flame that this is still significantly pressure dependent. And a lot of these guys have energies, when they're formed, they have energies up here, which are above these barriers. So all these reactions can happen. And what you actually see a lot of is this one. So here, the barrier is there. That's the lowest barrier, and then it goes to here. And for some reason, this guy is the highest rate. So you see a lot of singlet methylene formed from this reaction. And the singlet methylene is red, and it makes the red and orange color in the flames. So this is a very significant reaction. And if you try to model this, now I can do the master equation just like before. These is my A and my B. This is my AB. This is the excited AB starts. But now I have a whole lot of reactions that can happen over here, all these different reactions. And each one of them has its own K. So instead of just having KD of E, I have KD1, KD2, KD3, KD4. And also I could go back to the starting material. So I have several different possible rates. And I just have to add them all to the master equation. So the diagonal term of the master equation now has a whole lot of different possible products. And then I have to write down differential equations for each of those possible products. And this is one where people have done very careful quantum calculations with several different methods to try to figure out all those barriers that I showed you on that previous potential energy surface. And then here's, people have done a lot of experiments in this because it's a very important reaction. And so these are all the different experiments done at different temperatures of this guy, and trying to figure, and also measuring the products. And they find they can get pretty good fits to at least this one here using this formula for delta E down. But it doesn't really work over here. So you get the idea of like, if you sort of in the ballpark, we can predict things, but it's not exactly right. And then if you go to higher temperatures and higher pressures, you see some really funky stuff. So you can see it looks like the rate goes down, no, sort of down with temperature, then up with temperature. This is actually a regular T-plot here. Kind of strange. And then these are models for how that should behave. And this is if you do it at low pressure, then the data all looks like this. This is a model by, I think, Klippenstein. And these are some older theoretical papers trying to do the same thing. And we have experimental scatter, right? Experiments aren't perfect either. Calculations aren't perfect. Who knows? And then here's the prediction. This is very important to know what product you'll make. So unfortunately, it doesn't say which one this is, but I think this is probably the CH2 singlet channel. This is a very important one. And these are how sensitive the results are. So the overall performance of these experiments are sensitive to this reaction. And there's a lot of different reactions here. See all these different reactions? And the results that they're measuring, how much OH they have at different times, depends on all these different things with different sensitivities. And so this is Joe Michael from Argonne's experiment. And so the way you can try to figure out what can I learn from the experiment and find out you're sensitive. At early times, you're sensitive to these two reactions, the original recombination rate and the formation of singlet methylene. And then at longer times, they're sensitive to the other reactions. And so they measured the OH time profile and put in those reactions and tried to see if they could actually understand what happened. Okay, let's go a little bit further. All right, so all I talked about so far was cases with a single well. However, unfortunately, most cases have more than one well because there's different isomers of the same molecular formula that can be formed. And so it can be really complicated. Let's see if we can see some, we'll just kind of show. So here's what the model looks like. Now I have two wells here, well 1 and well 2. So I have my reactant and reacting with something, it makes my well, and it can associate and dissociate. And then this guy can isomerize from 1 to 2 or back isomerize. And then this guy can just, go on to form products. And there's also a separate rate that this guy could go to products, but would say with a higher barrier. And up and down, we're exchanging energy with P of E prime, just like before. And so you can write down all the rates. So you should have a rate that R goes to well 1, R plus M goes to well 2, R plus M goes to products. And also, well 1, if you made some of this stuff, it should dissociate to all these different products. It should isomerize and also dissociate, make the products, make the reactants. If you started with well 2 and you heated it up, you should be able to make all this stuff. So there's all these different reactions are the reactions you would have in a Chemkin model for this process. And so I want to know rate coefficients for all these guys, and they all depend on temperature and pressure. And I want to compute them all. And usually I'll just use the exponential model. I'll use Leonard-Jones for the collision rate. I want to be able to compute all these things. And so I'll use RCAM theory, the microcanonical rate coefficients for all these steps over all these barriers. Variational transition state theory for this one because there's no barrier. I'll write down the master equation. Now I have to have an index for which well I'm in. So I have Ni to keep track of the wells. So I'll have M wells, NP products, M plus 1 eigenvalues because I include the reactants in that. I assume this model assumes that the product formation is irreversible. So it's gone. So I don't have to worry about it coming back. And then you can consider what would happen if there were no collisions. So you have zero gas, bath gas, you just do it in the vacuum. Everything would fall apart. You can then solve it. And so people do this a lot. And so this is very important for the formation of prompt NO. So you guys know about phenamore NO? Anybody? Okay, so NO is one of the regulated emissions from combustion. Most of it's formed by Zeldovich mechanism, which is nitrogen just reacting with oxygen. But then the fuel can also react with nitrogen to make NO. And that fuel reaction is pretty important to understand the fuel effects on pollution. So people are really interested in this. Fenimore speculated, I don't know, maybe he observed some reaction like this, that the CH somehow reacted to make HCN. Hansen's group and Bowman, they did some measurements of this. Yarkoni started doing calculations to try to understand how that reaction happened. More calculations. They predicted that the rate should be less than the observed rate by at least a factor of 100, so something's wrong with the calculations. Then MC Lin's group figured out that there was a completely different intermediate than people had thought before, HNCN, and actually does not make HCN, it actually makes NCN instead. This was completely shocking to people who worked in this field since 1971 to figure out 29 years later that actually the product was different than they thought. That caused quite a stir. And then Newmark's group actually observed that you see NCN experimentally. So that was interesting. So Lin was right. So this shows the theory, how I think rates are changing with time as people understand things better. And then in very recent years, there's been a ton of papers trying to understand what happens. However, like the NO is severely underpredicted, so something's wrong in the models. Then they figure out that the rate is actually 1 or 2 orders of magnitude higher than they thought it was. Anyway, this is like the science in progress here. It's still happening now. So here's the experimental numbers on the rate. This is probably like the disappearance of the CH. And these are calculations, the different theoretical calculations of how fast it should go away. This is the potential surface. So the CH reacts with the nitrogen. It makes this goofball HCNN thing. This thing can rearrange by moving the radical around. This can, this is a resonance form. These can react across by opening up to form the HNCN. And then the HNCN, some of it will go back to CH plus N2, but some of it can go forward to H plus NCN. If it does that, then it's likely to go on to make NO.
Are there two traces on that plot?
I don't know, but my guess is there are 2 different levels of quantum theory. Yeah. So Klippenstein and Harding calculated HNCN to try to figure out what the rate of this reaction is at the end. So this last reaction is barrierless. So they have to do variational transition state theory. So they calculate the shape of the potential to try to figure out which way the H would come in. It turns out there's like barriers in some direction, so it can't come in certain ways. It can only come other ways. This is important for trying to figure out where the dividing surface is. You have to know what the heck the geometry is of how it's coming in. This one, they used the CAST method, which is a fancy quantum method that's good for diradical systems. You have a very well-stretched bond. But they calculated a rates here, which was pretty much higher than the rate that was measured, observed experimentally. So then they said maybe our quantum method is wrong. So they did a lot of quantum methods. They did the cheap one, B3-LIP. It looked like this. They did CCSD. It doesn't look too much like it. The potential surface looks wildly different, actually. And then they did the CAST methods, and they look sort of like each other, but nothing like these. So the quantum chemistry doesn't know what the real potential looks like. So if you don't know what V of R is, then you can't calculate the rate. So I think they decided that this was the best that they could do for the V of R. They calculated the rates. The frequencies that are calculated are like wildly different between B3-LIP and CAST-BT2. So they had to recompute. Normally you would use density functional theory to calculate all the frequencies. But in this case, they find huge errors. So they do it a different way. And now when they do it, with this transition state, they actually get things that go right through the data points. So now we'll find we have a story that actually is consistent with the experiment, explains why the CH goes away and why you make the amount of NO that you see. Let's see about this. You can do it, as I said, you can solve the differential equations and master equations directly if you wanted to. And you can also write down the analytical solution because it's a linear system of differential equations, so you know the eigensolution. And so you have this master equation. It has a lot of eigenvalues, a lot of eigenvectors. If you have multiple wells and multiple products, you're trying to figure out how to go from that solution, all those eigenvalues and eigenvectors, to the phenomenological rate constants. So in this case, we said there were like 6 phenomenological rate coefficients, K of Tp, that I want to get. And for any T and P, I can calculate all the eigenvalues and all the eigenvectors for like 10,000 population states. And I have to figure out how to go from those 10,000 by 10,000 matrices to the 6 numbers I want. And it's not so obvious. And there's multiple discussions in literature about how to do this, and they all disagree. And the key is that the real time-dependent solution is multi-exponential. So if you look at the solution of a system of a large system of differential equations, this is a sum of a lot of exponentials, all with different time constants. But when I do a chemical reaction rate, say I only think that if I think there's only 6 chemical processes happening, I only at most expect a sum of 6 exponentials, because I think there's only 6 time constants to do with those 6 reaction rates. But if I have 10,000 in this sum, then there's like a lot more. So something's wrong. So you have to figure out what's your process of how to relate them. And what Klippenstein and Miller advocate is that you try to look for the slow timescales and say that slow timescales are chemistry and the fast timescales are collision. And that works very well at low temperatures. And so you have some really slow timescales down here, and these are different isomers of this surface. You can actually figure out the eigenvalues correspond to certain exact chemical processes and work out the rate coefficients for those time constants. However, as you go to higher temperatures, you get like a convergence that all the eigenvalues all sort of converge together into a big continuum, a big mess. And you don't know which eigenvectors and eigenvalues correspond to real chemical processes and which one correspond to collisional energy transfer. It's all mixed up together. And so when you can do the separation of timescales, you just pick out the chemical modes, the slowest modes, and you say they're all chemical. And if you're lucky, they're all well separated from all the rest of the lambdas. And then you can just take the slow modes and say that this is chemistry. And that's the sort of the normal modes of chemical relaxation, and you can go ahead and do an analysis that way. And so you have the notes, you can look at the equations yourself, but I suggest you probably read the Klippenstein-Miller paper. It explains about the different ways to do it. This is the analysis for this reaction. This is very important. So this is ethyl radical with O2. It forms a peroxy. This can rearrange to what's called a QOOH species with a radical over here. And then this guy can fall apart to make OH radicals. There's one possibility, like here. And if it does go on to make OH radicals, that will make the combustion continue. If it lives long enough to react with an O2, it'll cause chain branching. But it can also just fall apart and make HO2, which would sort of quench the reaction. So this is a very important branch species in ignition. And so for that one, they did the eigenanalysis. And you get kind of goofy things where 2 eigenvalues at a certain temperature, 2 eigenvalues sort of converge. And you get a jump where which eigenvalue corresponds to the chemical behavior is different. So you have to track the eigenvalues and figure out what's happening. And then you can also vary the pressure and see a similar thing happens. You get normal fall-off behavior for some of the reactions, but for some of the reactions you get kind of goofy little bumps, strange shapes of the K versus pressure. You see how it's like kind of, you see the little lumps in here? And these are because it's actually from a multi-exponential solution. But people have done the experiments, and so they actually can directly measure it. So this is like the yield of HO2 from ethyl, actually this is propyl plus O2, same kind of potential surface, and they can see a multi-exponential jumps, and then it slowly rises, and then it slowly falls. and then they can connect those back to the master equation analysis. So you can understand exactly what happened and do the theoretical predictions. So here's the theoretical predictions with the dotted lines. You can see they're pretty close to the experiment for OH. So they measure OH and HO2 formation here. There's another case, multiple well. It's kind of goofball. You have these like shallow wells, deep wells, lots of different possibilities, lots of chemical reactions where you start with propargyl, a very important radical in rich flames with the H atom. You get all these different possible products. Over here, a whole bunch more. And so you need to know all these rate constants. Again, if you have a system that complicated, when you do the master equations and consider the fact that each of these energy states has a different rate all the way up, and here, all these energy states, and all these energy states, you can imagine how complicated the whole solution gets. So just for a simple molecule like that, one reaction only involves 3 carbon atoms. Already, this is like a journal paper about what the heck is happening when the H atom hits the propargyl, because so many different possible things can happen. As you change the pressure, different things happen, and the temperature, different things happen. But there's a procedure now to figure it all out, and so you can track down all the eigenvalues and figure out some of them correspond to some of the isomerizations. At high temperatures, some of the wells equilibrate. So if you go back here, at high enough temperature, all 3 of these wells will equilibrate because the barriers are low. So you'll just have one species. That's the equilibrium of these 3 together. But at low temperatures, there'll be distinct species with distinct rates. Does that make sense? Yeah.
Should take into account the scientist stage, i.e. photochemistry.
That'll be even a nightmare. I'm just doing thermal. This is just thermal. It's still already really complicated. Yeah. You can do a similar thing with and triplets and all kinds of stuff. And you get these kind of funny non-monotonic rate coefficients. So this is the rate for this process increases with pressure, and then it goes down with pressure. And here it's just increasing pressure. So this one looks like a normal fall-off behavior, but these other ones are non-monotonic. So they can be non-monotonic in temperature and also non-monotonic in pressure. But we have mathematics to compute them all. And experimentally, they observe it. Non-monotonic Arrhenius plots quite a lot. And it's important to get that right, of course, in your kinetic model, because otherwise you'll be completely wrong about the temperature dependence, for example. And so this is just how horrible it gets. This is propargyl plus propargyl, which is usually the main formation of benzene in flames. Benzene's a toxic, dysregulated emission. It's mostly from this potential surface, which is so complicated that they can't even draw it in a single figure. But they worked it out. They figured out all different arrangements of the carbon atoms and how they can wiggle around, and then all different possible ways they can break apart. So you have these 2 CH3s come together. They form all these different goofball isomers that eventually form, I think, phenyl radicals over there somewhere. Where is it? Yes, I think this phenyl radical was H. So that's like the main product that leads to benzene. But it's via all these different ways. The H atoms are all hopping around. You're getting some 5-membered rings, some 3-membered rings, 4-membered rings. You got them all there. And they found all the barriers, all the saddle points for all these motions of the molecules and calculated the rates for all of them. And there you get the whole story about the overall process, reactions to products. That's what I want to know, right? And in between, you have all these isomerization reactions, which you usually don't care that much about. And then they can compare that to the experiments, and you get reasonable. And you can see you can predict how it would change with pressure. And you also have isomerization too. You can predict the branching. So if you started from this molecule, you pyrolyze it, you make some of these guys, they recombine. They actually form the 4-membered ring, the 5-membered ring, and then the 6-membered ring. And that's what you see at the higher temperatures. Probably too complicated to explain in a situation like this. If you want to get into this, Steve Klippenstein's code is Variflex. It does the variational transition state theory for barrierless reactions, and it also does the master equations to handle the multi-eigenvalue case, the multi-wells. However, this is research code not usable without personal training. So it's a mess. But if you're into it, if you're willing to travel to Chicago and spend a week with Steve, he'll teach you how to do it, and you can do it. but it's definitely not professional code. Mesmer is more professional. There's an open source project to try to keep this going. This does the master equations, but I think it does not do the variational transition state theory. There's another nicely maintained set by Barker at Michigan called Multiwell. This one does the master equations nicely. However, the solver is stochastic, which means that every time you solve it, you get a different result. And also, if you have a low probability event, you may not sample it. So this is not good for rare event rates. So personally, I really don't like the solver. However, everything else about this is really nice. It's very clear. It's great documentation. The master equations things are all written well. Barker's organizing round robins to compare codes and make sure everything's good, and you can predict everything correctly. For Riken and Peters and Leuven, they have the steady state solver, so they assume if you make the steady state approximation on a lot of the species, then you make the whole thing from a differential equation into like a linear system of equations. And then you can solve it, even if it's very stiff. So that's that method. ChemRate does the diagonalization and then reports the time-dependent solution with the multi-exponentials. And then you're left on your own to figure out how to turn that into the chemical reaction rates, which can be pretty hard. But sometimes it's clear. Sometimes it'll just be obvious that there's one eigenvalue that's completely different from everything else, and it's the chemical one, and you're done. But if you have multiple eigenvalues, it's really difficult to interpret this. But this is also, it's got a pretty interface. It's nice. And then the RMG program I have has a modified strong collision solver, which is pretty good. It has another method that was suggested by one of Pilling's students that works for certain cases with deep wells. And then it also has the method that Klippenstein and Miller recommend, this multi-eigenvalue thing. But it doesn't have quadruple precision. So if you have a case that's too stiff, it'll crash. But if your system's not too stiff, you'll get the same result as Klippenstein. And for the and then in general, you can always run the modified strong collision. You always get something that's reasonable, but it may be off by up to a factor of 3 from the real solution.
Does your code require person training?
No, so mine is actually made totally automatic, so it'll try to estimate all the rate constants for you and everything, so you don't have to do anything. However, the estimates may not be that accurate. So if you really want accuracy, my code might not be what you want. But if you want something easy to use, mine's definitely it. You just press in A plus B, go, and it'll tell you all the products. It'll tell you estimates, how they depend on pressure and temperature. And so for a first guess, I would say mine is definitely preferred. It won't take any of your time. Then when you decide you really care about it, then it might take you a long time to figure out how to do it exactly right. Yeah.
Open source?
Yeah, it's open source. Yeah, RMG, sourceforge.rmg.net or something like that. You can just type RMG. And it has some documentation. And it's been used by 30, 40 users. So some of the bugs have been worked out, and some of the features actually work well. So it's sort of a it's not professional code, but it's for sure better than Veriflex. So as far as professionalism. If you do want to get into it, I would recommend you maybe come to MIT and spend a few days there, and my students can help you to use it and learn about all the options and what all the outputs mean. You get a lot of output you run a master equations like this. If you have 100 different possible products and 4 different isomer wells, you get just tons of data output, and then trying to even understand what you did might give you a headache. So it's good to work it through with somebody, hold your hand the first time to understand. All right, let's take a break.